Alright, today we're looking at our Dynamics Forces Revisited review, and we're going to walk through every problem, talk through them, and see how to solve them. Alright, number 1. Normal force is not always equal to an object's weight. Give 2 examples for when the normal force is not equal to an object's weight. Well, of course we had our elevator problems, and we said, if you're in an elevator, it'd help if I turn my pen on. Say you're in an elevator, and here's you. And if you are accelerating upward, the only way you accelerate upward is if you have some total force upward, more force up than you do down. So we'd say, if you're accelerating upward, you have your force of gravity. Your normal force must be bigger than your force of gravity. These are the only 2 forces acting on you. Your normal force must be bigger than the force of gravity. And remember, force of gravity is the same thing as an object's weight. Now, what if you're in an elevator and you're not accelerating upwards, you're accelerating downwards? Maybe you're on the top floor and you start moving down. What does this look like? Well, force of gravity is set. Your mass and your acceleration due to gravity are the same. You're still on Earth, and your mass is the same as you're riding the elevator. So your force of gravity stays the same. I've drawn it relatively the same size. These are supposed to be equal. Again, our force of gravity right here and our force of gravity right here, those are equal. Your force of gravity is not changing, but to accelerate downward, you need more force down than you have up. So our normal force is going to be smaller than that force of gravity. That's what lets us accelerate downward. Number 2, draw a free body diagram and explain in full sentences why you feel heavy when an elevator first accelerates upward when you go from the 1st floor to the 5th floor of the building. Well, this is what we had just talked about right here. Your sensation of heaviness really comes from your normal force. So, when the elevator is pushing you upward really, really hard, you feel very heavy. You feel kind of stuck to the floor. This sensation also happens in roller coasters. If you are accelerating upward a lot, you feel kind of stuck to your seat. Your normal force is bigger. That gives you that sensation of heaviness. And the opposite actually happens when your normal force shrinks, right? When you're accelerating downward and your normal force is smaller than the force of gravity, you feel very light. This is like arriving at the top floor in an elevator. When your elevator slows down and you slow down, your normal force shrinks. It's smaller, you feel lighter. This even ties back to our talk about astronauts and their sense of weightlessness. They still have weight. They still have a force of gravity acting on them from the Earth, but they're no longer really touching a surface. There's no normal force. They're continuously falling. If there's no normal force, they are weightless. They feel weightless rather than they are weightless. Astronauts do experience gravity when in orbit around the Earth. The phrase zero gravity leads to a common misconception. We actually just walked through this. I didn't even know this was the next question. Astronauts in the International Space Station, or just astronauts in orbit, they experience this feeling of weightlessness because they're really constantly falling around the Earth. It just so happens that they fall at the same rate the Earth curves, so they're never getting closer to Earth's surface. They're perpetually falling. They still have that force of gravity acting on them, but there's no normal force to balance, and normal force is what gives you your sense of weight. And before moving on, this last sentence explains why astronauts appear to float while the International Space Station orbits Earth. Well, they appear to float because they are moving with the space station. Right? The space station is also orbiting Earth. It's in this constant state of perpetually falling around the Earth, just like the astronauts are. So, when the astronaut is moving at the same rate and in the same direction that the space station is, it looks like they're not moving at all. If you think about when you're in a car, looking at your surroundings in the car, it looks like they're not moving at all. You're not moving, they're not moving, nothing's moving. But if you look outside, it becomes apparent, you, the car, everything in it are moving. Alright, you're in an elevator standing on a bathroom scale, 1 units of newtons, and experience a 3 meters per second acceleration downward. If your mass is 60 kilograms, calculate what the scale rates. Our general approach for solving forces problems is going to be, we draw our free body diagram. Well, we're in an elevator. We're on Earth. There's a force of gravity. We also know, we're on the floor, there's a normal force. Now, a question that we have to ask, how big do we make this normal force? We know we are accelerating downward. We should be comfortable with the idea of, whatever direction you're accelerating, that's the direction your total force points. Unbalanced forces cause acceleration in the direction of the unbalanced force. So if we're accelerating downward, we have unbalanced forces downward. Gravity must be bigger than our normal force. So we'll make sure that's reflected in our free body diagram. It's unbalanced downward. We drew our free body diagram. Step 2. You should have 2 equations you can write for your free body diagram. The first one is Newton's second law. F total equals ma. You can always write that one. That's given to you. You don't have to memorize it. We give it to you. The next one, you have to write your own equation. You can call this your total force equation, your sum of forces equation, but no matter what you call it, what you're doing is always the same. Take your forces in the positive direction, so your normal force, and you just write them. If you had multiple forces in the positive direction, you just add them all together. And then take forces in the negative direction and subtract them. So your total force is, whatever the normal force is, minus your force of gravity. And then you want to combine your equations and write out, okay, if we combine, plug in, replace F total with ma, you get ma instead of F total is equal to the normal force minus the force of gravity. And you're going to always follow really these 3 steps for whatever forces problem you tackle. Now, if it's something like friction or skydiver, the problem solving process can diverge. You're not always going to do the same exact thing, but to help you get set up and be able to go from a solid basis, you should always follow these 3 steps. Write out your free body diagram, write your 2 equations, and then combine your equations. Now you have a really good basis to start solving your problem. Okay. Now we're really just going to plug in and see where we get. We know we're solving for what the scale reads. And we need to identify, okay, what the scale reads. That means normal force. We're asked to solve for our normal force. That's what the scale reads. Well, and at this point you could plug in, but I'm going to go a little farther and just use our variables. We know the force of gravity is just m times g. So why don't we plug that in for our force of gravity? You rewrite your equation, mass times acceleration, is normal force minus mg. And now at this point, really there's nothing else we can do. We have normal force, we have our mass, our acceleration, our mass, and our acceleration due to gravity. Plug this in and we can solve. We'd go ahead, we'd plug in, okay, mass is 60 kilograms. Acceleration, 3 meters, let me move this. Because we know we're accelerating downward. This should be a negative acceleration. Normal force is what we're solving for. Mass is 60 again. G is our 9.8. And now we just have to go ahead, we use our calculator, we can solve. We'll go through, and you can do this as well, make sure you're getting the same answer. 60 times negative 3 gives us negative 180, equals our normal force, minus 60 times 9.8, that gives us 588. Add our 588 over, and we find out, okay, you get 408 is equal to your normal force. And now, of course, you should add in, it's a force, so we measure our forces in units of newtons. Now you can always double check. Your force of gravity is 588. Your normal force is smaller than your force of gravity. Does this match what we know? Well, we're accelerating downward. To accelerate downward, you need more force down than up. So your normal force should indeed be smaller than the force of gravity. And in fact, we know that just from drawing our free body diagram. All right, normal force is smaller than force of gravity. That checks out with our answer. Always good to double check. Number 5, calculate the force of kinetic friction acting on a 90 kilogram object as it slides. Coefficient of static friction is 0.55. Coefficient of kinetic friction is 0.38. Okay. Here, coefficient of kinetic friction. I like to start with identifying what we're trying to solve for. Calculate the force of kinetic friction. Okay, let's look at our equation. Our equation, the force of kinetic friction, is our coefficient of kinetic friction multiplied by our normal force. Let's identify what we have. We have our coefficient of kinetic friction right here, 0.38. That's what we're going to plug in right here. We just need our normal force. If we have our normal force, we can plug in and solve. Well, let's think about our free body diagram. What forces would act on an object? We know it's sliding across some surface. There's gravity, there's normal force. Now, we don't really have any information about what's happening horizontally. And it turns out we don't really need it. Because we know for an object sliding horizontally, it's not accelerating vertically, the forces must be balanced. Normal force is equal to our gravity. Gravity is equal to m times g. So if we plug in our mass, 90 kilograms, and 9.8 for our g value, that gives you the force of gravity. 90 times 9.8. Okay, your force of gravity is 882 newtons. But we know your force of gravity is your normal force. So we can plug in for our normal force our 882. Let's rewrite. Force of kinetic friction is our coefficient of kinetic friction. That's our 0.38. And we're multiplying by that normal force, which is also our force of gravity in this problem, 882 newtons. 882 times 0.38 gives us a value, our force of kinetic friction, 335.16 newtons. Alright. 6. Calculate the force necessary to budge the object from rest in the previous question. Alright, to budge. This means it was at rest. When it's at rest, it's experiencing static friction. To break static friction, to get an object to move, you have to push with more than that maximum value of static friction. So this problem is really telling us, solve for your maximum value of static friction. You'll need to push more than that to overcome your static friction. So, set up our equation. Coefficient of static friction times our normal force gives you that maximum static friction value. Lucky for us, we just calculated our normal force. It is still 882. Our coefficient of static friction, it's different. It is 0.55. And we are no longer using that coefficient of kinetic friction. We're saying the object is not moving. We use static friction. Find your answer here, 882 times 0.55. Gives you an answer, 485.1 newtons. So, how much force is necessary? More than 485.1 newtons. Alright, number 7. You push a stack of physics textbooks across a table. What else would you do with them? Exactly. The force of friction between the books and the table is 8 newtons. The books have a mass of 15 kilograms, and they accelerate at 0.2 meters per second squared while you push. Draw a free body diagram, like we always want to start out with. Well, we know it's sliding across a table. It's on Earth. There's gravity. It's on a table. There's a normal force. It's not accelerating vertically. These forces must be balanced. They accelerate 0.2 meters per second while you push. So they are accelerating. So we know, okay, well, we are pushing. There's some applied force, Fa, or F if you prefer. We also want to make sure we have friction. We are even told there is this force of friction, so make sure we draw it in. Be careful. We want to make sure this is kinetic friction because it's sliding. If something's moving, it experiences kinetic friction. And we know that friction should be smaller than the applied force because it is accelerating. Calculate the applied force on the books. Okay. How do we do this? We don't have an equation for the applied force. Well, here's where that second step I went over earlier comes in. Right, recapping. Draw your free body diagram. Write your two total force equations. Then substitute them in, combine your equations. So our second step, write out your two equations. F total equals ma every time. And F total, you want to identify if you have forces in all your directions. Identify where they're unbalanced. We know, okay, just looking at this free body diagram, normal force and gravity are balanced. Off to the side, we could even jot down a little note to ourselves. The normal force and the gravity are equal. If we ever need that, it might come in useful. But what we're really paying attention to is where are they not balanced? That's where we want to direct our attention. And here we see, okay, clearly they're not balanced horizontally. That is what we use for our equation right here. Look at your horizontal direction wherever they're unbalanced, and write what are your positive forces. Well, we have the applied force acting to the right, to the positive direction. We list it as positive. Kinetic friction acts to the left. We list it as negative. Applied force minus kinetic friction is your total force. Combine your equations. Mass times acceleration. Another way to write total force is your applied force minus kinetic friction. And now we start to see, okay, applied force is our end goal. Our end goal is to calculate the applied force. Well, applied force, it shows up in our equation. If we can just solve this equation for applied force, we'll have our answer. So what do we need to get there? Well, we need our mass. Okay, we have that. Our mass is 15 kilograms. We need our acceleration. We have that, 0.2. Our applied force is what we're solving for. We need our kinetic friction. We have that, it's 8 newtons. You have everything with this to now just go ahead and solve. 15 times 0.2 gives you 3 equals the applied force minus 8. Add 8 to both sides, we get that the applied force is 11 newtons. Okay? Calculate the coefficient of kinetic friction between the books and the table. Well, kinetic friction. Calculate the coefficient of kinetic friction. Coefficient of kinetic friction only shows up in one equation. That is, our force of kinetic friction is equal to our coefficient of kinetic friction times the normal force. To solve for coefficient, we need two things. We need our kinetic friction, and we need our normal force. Now, kinetic friction, we already know. This was given. It's 8 newtons. How do we find the normal force? Well, on our free body diagram, normal force and gravity are balanced. We even wrote out our equation right here. Normal force is equal to gravity. They're balanced. So, solve for your force of gravity, m times g, and you'll have your normal force to plug in. The mass is 15. G value on Earth is 9.8. 15 times your 9.8. 147. Whoa, 147. Let's make this a better equal sign. Okay. Plug this in. And now, of course, we're going to take 8, divide by 147, isolate our coefficient. We find, okay, our coefficient of kinetic friction is something really small, 0.054. There's no units. Make sure you're not putting units on your coefficient of friction. Coefficients do not have units. At least your coefficient of friction does not have units. Alright, number 8. You're moving into a new house and your friend is helping you push your new oven across the kitchen. What a good friend. He says, if we push harder, the oven will move faster because the friction on the oven will be a smaller value. Using what you know about the equations to solve for the force of friction, explain why your friend is incorrect. Well, we give you a massive hint. Use what you know about the equations. Let's look at our equation. Well, the force of static friction, the max value, is the coefficient of static friction times the normal force. Now in this problem, we are saying the oven's moving. So more aptly, we really want to look at our kinetic friction. Mu k times the normal force. Coefficient of kinetic friction times the normal force gives you your kinetic friction force. And what we'd say looking at this equation is, well, what does it depend on? Your coefficient right here. I tried to make that a squiggly arrow. It didn't really work out. Let's try one more time. That's better. Okay. Your coefficient of friction. What does that depend on? It depends on the roughness of the surface. And that's it. Literally just a measure of how rough the surface is. Nothing else. Normal force. This generally doesn't have to be, but most of the time in our problems, we are saying our gravity and our normal force are balanced. When we're pushing something horizontally, gravity and normal force are balanced. So this is really more a representation of how the surfaces are interacting, how they're pushing on each other. There is nothing about pushing harder, the oven moving faster, because friction decreases. Look at your equation. Friction depends on your coefficient, the roughness of the surface, and the normal force. Doesn't depend on how fast it is moving. That's air resistance. Air resistance does depend on how fast you're moving. Friction does not. Alright, let's get started on our next one. Two children push a 15-kilogram box together on a carpeted floor. The bigger child pushes with 20 newtons. The smaller child pushes with 10. Unknown frictional force opposes the motion of the box. Box accelerates at 0.2. Okay. Free body diagram. Always our first step. Gravity. Normal force. They balance. We're pushing something on a horizontal surface. These will always balance when you are pushing something on a horizontal surface. You have your applied force. There's the applied force of the bigger child. Maybe we'll say F-A big for a bigger child. And we'll do a smaller arrow. This could be F-A small for our smaller child. We know there's friction, and it is opposing the motion. Well, the box is moving in the direction the children are pushing, so friction acts opposite. It is moving, so we need to be able to identify that's kinetic friction. Kinetic friction acts when the object is moving. Okay, we drew the free body diagram. Calculate the force of gravity. Well, we always said free body diagram, then write out your two equations. Identify what's balanced, what's unbalanced. You might come back to this later. Let's write out our equations. F total is equal to mass times acceleration. And which way are we unbalanced? We're unbalanced horizontally. So that's what we'll use to write our custom equation. F total is the applied force from the big kid plus the applied force from the small kid minus our force of kinetic friction. All I did was I listed our two positive forces as positive, and I subtracted the force acting in the negative direction. You could combine these equations and say, okay, mass times acceleration is the force applied from the big kid plus the force applied from the small kid minus your force of kinetic friction. We'd also be able to write out, what about our vertical direction? What do we know about that? Well, normal and gravity are balanced. We could write out our normal force is equal to our force of gravity. Here we've written two very important equations that we'll be using, and the way we wrote them both is just from our free body diagram. Okay. Force of gravity. Where does this show up? Well, even if we hadn't written out these equations, we're just looking at our free body diagram, we should recognize normal force is equal to gravity. So, calculate. Oh, I thought this said the normal force. It doesn't. It says force of gravity. So, force of gravity, it is the normal force. We'll keep that in mind for later. The force of gravity, Fg equals mg. Your mass is 15. Gravity is 9.8. We did this earlier. This gives us 147 newtons for our force of gravity. Alright, normal force. Normal force is the force of gravity. 147 newtons. Don't even need to show any work. Force of friction. Well, where does that show up? Force of friction is right here. Okay, let's write that equation in. Mass times acceleration is the applied force from the big kid plus the applied force from the small kid, subtract that friction. We know the mass. It's 15. We know our acceleration. 0.2. Applied force from the big kid, 20 newtons. Applied force from the small kid, 10 newtons. Friction. That's what we're solving for. Use this to solve. 15 times 0.2. I believe that is 0.3. Not 0.3. I mean, my brain is not working. 3. Excellent. So we could take this. We say, okay, in blue, this is 3 equals 20 plus 10 is just 30 minus your force of kinetic friction. Rearrange, and you'd say, well, if you subtract both sides, subtract 30 from both sides, you get negative 27 equals your negative force of kinetic friction. So your force of kinetic friction is 27 newtons. Coefficient of kinetic friction. Write out your equation for kinetic friction. The force of kinetic friction is your coefficient times your normal force. Plug in what you just had, 27 newtons. Your normal force is 147. We're multiplying this. Go ahead and divide 27 divided by 147. We should get our coefficient of kinetic friction 0.184 if we round up to our thousandth place. If you rounded 0.18, that would be totally fine as well. Alright, number 10. You hook a force probe up to a 0.35 kilogram wooden block placed on a wood table. You pull on the force probe and move the block at a constant speed of 0.15 meters per second. You measure the probe force to be 2 newtons. Calculate the coefficient of kinetic friction between the wood block and the wood table. So here, very, very important, we're moving at a constant speed. It would help if I turned on my pen. Constant speed. That means we're not accelerating, we're not speeding up, we're not slowing down, we're not changing direction. Our forces must all be balanced. So we have our gravity, our normal force, these balance each other. And then we'd say, okay, we're pulling. So there's some applied force. And we know there's some friction. And our applied force and friction must be balanced. Again, we know that because of the constant speed. So applied force is equal to friction. Calculate the coefficient of kinetic friction. Well, that shows up in our equation for kinetic friction. It is the coefficient of kinetic friction multiplied by our normal force. We know our force of kinetic friction from our free body diagram right here. Applied force is equal to the force of kinetic friction. Our applied force is 2 newtons. So we can plug this in. Now we just need to find our normal force and we'll be all set. Well, our normal force, it's balanced with the force of gravity. So Fn equals Fg. Force of gravity is m times g. We know our mass, 0.35. We can plug that in, multiply it by 9.8 to get our force of gravity, which is our normal force. Let's grab our calculator, 0.35 times 9.8. And we get that normal force, 3.43 newtons. Plug that in. Divided by 3.43. Coefficient of kinetic friction, 0.58. Remember, there's no units. Number 10, heavy box sits motionless on a table. A small child pulls on the box with 25 newtons of force. The box does not move. All right, box is not moving. The free body diagram, forces acting, must all be balanced. Force of gravity balances the normal force. Applied force, the child is pulling,
box does not move. Again, we know that's balanced. It's not moving, so we'll say that this friction is static friction. Well, how big is static friction? It's just as big as the applied force, right? The applied force is equal to that force of static friction, 25 newtons. And that's it. Nice and simple. Number 12. Tourist drops a penny, 0.0025 kilogram penny from the top of the Willis Tower. Draw the free body diagram, calculate all forces, and calculate acceleration when the penny is initially released. All right, this is dealing with air resistance. Well, draw a free body diagram, calculate forces, calculate acceleration. Okay, penny is initially released. It's not yet moving. The only force is gravity. Oh, we have space. Let me put that here. Free body diagram. Only force, gravity. How big is that force of gravity? Well, Fg equals mg. We can plug in the mass, 0.0025, multiplied by 9.8, and we get that force of gravity 0.0245 newtons. And we know that force of gravity is not going to change, right? The mass of the penny stays the same as it's falling. So I'll draw in, oh, pardon my dog. So I'll draw in force of gravity. It's the same at each point in the drop. Okay. And now we just need to keep going. So for our first one, penny is initially released. We know, okay, what's the acceleration? Well, the only force acting is the force of gravity. When the only force acting is the force of gravity, the acceleration is 9.8 meters per second squared. And we, of course, know that acceleration is downward. If we have an air resistance, here it is, F air, of 0.012 newtons, well, total force is the air minus force of gravity, so 0.012 minus 0.0245, negative 0.0125. Divide your total force by the mass, 0.0025, to get your acceleration. 5 meters per second squared down. That's why I'm not writing the negative. I'm just writing that it's down. This makes sense. The total force is smaller because now there's air opposing our gravity. Acceleration is smaller than it was before. Penny has reached terminal velocity. Well, terminal velocity, that's a key word. That means the air resistance is equal to the force of gravity. There is no total force. The total force is 0 newtons. The acceleration is 0. Our forces are balanced. Fg equals F air. So that air resistance must also be 0.0245 newtons. Okay. And number 13, a bowling ball is dropped off a cliff. Will air drag ever get larger than the force of gravity? Explain your answer and discuss the velocity and acceleration of the ball once a lot of time has passed. No. You drop your bowling ball. It starts off. The only force acting is the force of gravity. It's accelerating downward. Then, let's move this down so I have a bit more room. Let's copy this over. A bit later, you have picked up some speed. The bowling ball is falling. It has some air resistance. That total force is a bit smaller because some of the gravity is canceled by the air resistance. It's still accelerating downwards, but at a bit of a smaller rate. The acceleration is not as big. A bit later, again, your force of gravity is not changing. But since you're going faster, your air resistance has grown. Again, you're still unbalanced downward, you're still accelerating downward, but not as fast. And eventually, you reach a point where you are finally going fast enough that your air resistance is the same as your force of gravity. These balance. That's your terminal velocity. Right here. And now terminal velocity, you are never going to speed up beyond that. Your forces are balanced. Balanced forces mean no acceleration. You are just at your terminal velocity. If you're falling for an hour, you are just still at your terminal velocity. Number 14. You drop 2 bricks with equal surface area. One is made of a lightweight plastic, and the other is made of lead. Eventually, both of them are moving downward at terminal velocity. Which brick has the bigger force of air drag acting on it during terminal velocity? Well, again, we know terminal velocity means the air resistance is equal to the force of gravity. Compare the force of gravity acting on the plastic versus the lead. Force of gravity on lead is bigger than it is on the lightweight plastic. These forces of gravity will be balanced with the air resistance. So, the bigger force of gravity also means the bigger force of air resistance at terminal velocity. All that to say, air resistance is bigger on the lead. Calculate the force of gravity on the moon using Newton's universal law of gravitation. Okay. FG, let's make sure we're still recording. Excellent. Is big G, M1, M2 over R squared. Plug in, we know G is 6.67 times 10 to the negative 11th. Mass of our first object, let's say it's the Earth, is 6.0 times 10 to the 24th. And second object is the moon, 7.35 times 10 to the 22nd. Okay. Divide by the distance between them. Distance between their centers, it's given. 3.844 times 10 to the 8th. Remember, we have to square this. So square that. Let's jump into our calculator. That's Notability, not our calculator. Try it one more time. Here we go. All right. 6.67 times 10 to the negative 11th. Multiply by 6 times 10 to the 24th. Multiply by 7.35 times 10 to the 22nd. Divide by 3.844 times 10 to the power of the 8th. That whole thing squared. Double check. Aha. I knew this didn't look right. I accidentally put in, let me do this right here, I actually put this in as a positive 11th power. That should be negative. Let's redo it. 6.67 times 10 to the negative 11th, much better, times 6.0 times 10 to the 24th times 7.35 times 10 to the 22nd. Now we divide by our 3.844 times 10 to the 8th. This whole thing is squared. We get our answer. Force of gravity is 1.99 times 10 to the 20th newtons. Now, of course, you could round this. Really, this is 2.0 times 10 to the 20th newtons. Okay, that was the force of gravity on the moon force acting on the moon from the Earth. What is the force on the Earth from the moon? Well, Newton's third law. Every action force has some reaction force. So if the Earth pulls on the moon 2 times 10 to the 20th newtons, the moon pulls on the Earth with that same force. 2 times 10 to the 20th newtons. There we go.